Today we will begin looking at continuity. To begin, a function is continuous over a given interval if you can draw the function without lifting your pencil over that interval. No break, no jumps. So example 1, state whether each is continuous or not. I have gone ahead and already filled this part in for you, but let's go through it together. So in our first example here, in A, we look at this function and you see that it is continuous. The reason being is there's no jumps and no breaks. That is because we can follow along and trace it and never have to lift our pencil. Therefore, it is no breaks, no jumps, and continuous. Our next example, in B here, this is called point discontinuity at x equals -2. That's because we have a hole. As you notice, if I go ahead to draw my function, I have to lift my pencil and begin on the other side of -2. In C, we have jump discontinuity at x equals -1. This shows that one-sided limits aren't equal. Again, I can draw my function, but when I get to 1, I have to stop and jump up to the top to continue my function. And our last example is infinite discontinuity. We have an asymptote here at x equals 2, and then we have our function on either side. Therefore, we can't keep our pencil on the page and continue. Another type of discontinuity. So to summarize, when a function is continuous or not, the function f at x is continuous at x equals a if f at a is defined if the limit of f at x as x approaches a is equal to f at a, and the limit of f at x as x approaches a exists. Otherwise, f at x is continuous at x equals a. We will now continue looking at example 2. Graph f at x, where when x is greater than or equal to -1, f at x is equal to x squared minus 1. And when x is less than -1, f at x is equal to 2x plus 2. So we're now going to go ahead and graph this. So for x squared minus 1, we know this is just a parabola with, it's been translated 1 down. So we know our parabola is going to have our points using our step pattern. You always start with your vertex, which is at 0, -1, over 1, up 1. We get our point to be 1, 0, over 1, up 3. And we could go on and on, but that's enough points. We're not going to go any further to the left except for when x is equal to -1, because that's where it stops. And now we're going to look at 2x plus 2, and this is just a linear function. So at 2x plus 2, when x is equal to -2, we can sub that in. So it would be 2 times -2, which would be 4, -4 that is, and -4 plus 2 would be -2. Okay, and we know we'd also have our point at -1, 0 as well. And this would just be a straight line. So this is what our function would look like. So in part B, we want to look at what the limit of f at x is as x approaches -1. So to do this, since it's a piecewise function, we're going to look at the limit on the left and right hand side of -1. So first we'll look at the left side. so as x approaches 1 from the negative side, and as x approaches 1, or sorry, negative 1 that is, from the left side, f at x will be equal to 0. And as the limit approaches negative 1 from the right side, so our positive side, we know that f at x will also be equal to 1. Therefore, this limit does exist, since from the left and right hand side are both equal to 1. So therefore, the limit of f at x as x approaches negative 1 will be equal to 0. And therefore, we also know that this is also continuous. Okay, as I trace over our function here, you'll notice I never actually have to pick up my pen. So in part C here, we want to look at when our value of a is negative 1, or value of x. So f at negative 1. We can just sub that negative 1 into our equation here, or you can look at it on the graph. And you notice on the graph here, our point is at negative 1, 0. So therefore, f at negative 1 is going to be equal to 0. And again, we know this is continuous. Now, for example 3, we want to test the continuity of each at x equals 2. If the function is not continuous, I would like you to state why, and we will do that as we go through each of the examples. So for part A, we have f at x equals x cubed minus x. So since we want to test when x is equal to 2 here, we're just going to actually sub that value in for our x value. So we're going to sub it in, so f at 2 equals 2 cubed minus 2. We know that 2 cubed is 8, 8 minus 2 will be 6. So therefore, the limit as x approaches 2 of x cubed minus x is going to be equal to 6. So therefore, this is a continuous function at x equals 2. Similarly, we're going to just again sub in 2 for our x value. So we have 1 over 2 minus 2 squared. This will be equal to 1 over 0. Anytime that we have a denominator of 0, we know that this is therefore undefined. So since it's undefined, we know therefore not continuous. At x equals 2. And this is because of it being undefined. For C here, f at x equals x squared minus x minus 2. We're going to first factor this. So we have f at x is equal to x minus 2 times x plus 1 over x minus 2. You'll notice here that we can cancel these out. So since we're able to cancel those out, we know that this is therefore not continuous at x equals 2. The reason being is anytime we cancel out from the denominator and numerator a whole term, we know therefore there's a whole. Okay, so that's why this function isn't continuous at this, because we would, if we actually graph this, we'd have an open circle at 2. So therefore, f at 2 is not defined. So next we have a piecewise function. So with a piecewise function, I always like to draw what my graph looks like. So we would have something similar to looking like this, where we would have our parabola for 4 minus x squared when x is less than 2. So this right here would be our value of 2. And when x is greater than or equal to, we have a value of 3. So we would have our whole function here looking similar to this. So you'll notice for our parabola here, when our x value is 2, okay, our y value is 0. So that point there, this point here, is going to be 2, 0. Where this point right here is actually going to be 2, 3. Therefore, you can see that there has been a jump. So since the limit as x approaches 2 from our positive side of g at x is equal to 3, and the limit of g at x as x approaches 2 from our negative side or left side is equal to 0, therefore this does not exist. And therefore, this is a jump discontinuity. Now, in example 4, we want to create a function f at x that has a jump discontinuity at x equals 2, and the limit of f at x as x approaches negative 1 is equal to f at 2. So therefore, I know that since it's a jump discontinuity, we know it's going to be a piecewise function. So I like to actually graph this first. Okay, there are many examples that you could be using for this. I'm going to choose to use some linear functions. So if we're looking at when x is equal to 2, I'm going to have my function here, okay, where I'm choosing that I'm going to have a linear function of x. Okay, so my function f at x, I'd have x for when x is less than or equal to 2. And then I'm going to say 3. And I'm just going to have another linear function. So I'm going to say my f at x is equal to 3 for x is greater than 2. So you'll notice here that we have a jump discontinuity where the limit of f at x as x approaches negative 1 is equal to f at 2. Now in our last example, example 5, we're going to create a function f at x that has jump discontinuity at x equals 2, and the limit of f at x as x approaches negative 1 is not equal to our f at 2. So what is the difference between example 4 and example 5? The only difference is the fact that this one here is not equal to. So why it's not equal to, all that's stating is that it doesn't exist at all at our value of 2 for our x. So when I draw this, I'm going to choose to have 2, 3, 4, 1, 2, 3. I'm going to have my function, I'm going to do 2 linear simple functions here. Where my f at x is going to be equal to 1 for x is less than 2, and my function is going to be equal to 4 for x is greater than 2. So you notice here that these are both open, so circles, so that means that it's never actually equal to 2. And therefore we would have a jump discontinuity at x equals 2, and our limit of our f at x will not be equal to our f at 2 because of it not being included.